Okay, let's get started with the RowHammer finally. So I have a lot of slides. I'm not sure if you're going to be able to cover all of them in the remaining 1 hour 28 minutes, but let's try. So I'm going to talk about RowHammer, and I think this is an example of multiple things. One is a real evidence of the fact that DRAM scaling is getting really, really hard, and the second is it's actually the first example that I know of a hardware circuit level failure mechanism, reliability mechanism, that leads to a widespread system security issue. This connection between reliability and security has always been very interesting from the perspective of people in general, and we will talk about that when we get into the depths of the lecture. But this is the first real example of a hardware level fault, let's say, affecting system-wide vulnerability. And we will see that. That's why I like this. This is really fascinating, I think. And I believe there will be more connections into the future, people finding all of these hardware level faults leading to security vulnerabilities. Of course, hopefully the defenders will be careful, right? They will understand how they will build mechanisms to defend against these, and that's going to be part of this lecture also, not just the problem but the solution directions. And I think that solution direction mindset is really important. How do you design your system such that even though the hardware may be unreliable, and you will run into a lot of unreliability issues, how do you actually still make things run more secure and even reliably? How do you give that reliability even though the underlying hardware is unreliable? Okay, so that's the first direction basically. Fundamentally secure, reliable, and safe architectures. These are three different things actually: security, reliability, and safety. Right? We can have a discussion on that. I don't want to have that discussion right now. But safety is, for example, you don't want to have an accident on the road. Reliability is you don't want to get bit flips, and security is you don't want to get compromised, right? That's actually a good way of thinking about it. And with the RowHammer, all of these things come together. Reliability issues can demonstrate themselves as safety problems and security problems, but not all reliability issues can be exploited for security, and not all reliability issues necessarily cause safety problems, right? But I think in RowHammer, this reliability problem is actually causing both safety issues, potentially, depending on when this occurs, and security problems. Okay, so basically I'm going to tell you the story of RowHammer, and at the high level, this is the fact that you can predictably induce bit flips in commodity DRAM chips that are used in the field. And when we first did the studies, we found out that more than 80% of the DRAM chips are vulnerable to this reliability mechanism, or failure mechanism. And it's, as I said, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If someone finds an earlier example, please let me know. I think it's good to set the record straight. If this statement is not true, I'm happy to revise it. Okay, but so far this didn't need revision. And that's why I think people are, in a sense, excited about it, saying you should forget software. Hackers are now really exploiting physics. This will become more clear in a little bit. But I will also motivate this in a different way. Does anybody know who this is? Don't use the side channel information. Clear, there's a side channel information over here. His name is clear, Maslow. Does anybody know who Maslow is? Yes? Okay, who is he? Anybody? Yes?
I know him because he's like the hierarchy.
Exactly, he's more famous for this thing, right? Probably. Where do you know him from? Like what course or?
Just in general.
Just in general, yeah. Yeah, he has had a lot of impact in the field. That's why you know him very well, right? He's a very famous American psychologist, Abraham Maslow, and he was very interested in why human beings do the things they do. You can see that he dedicated his life to understand that question basically, and he basically kept revising his book about that. And you can see this is one of its earlier papers over here. But basically he is very famous for this hierarchy, and for good reason. Basically this hierarchy states that you need to have your basic needs satisfied before you can think about more psychological needs, esteem needs, and before you can think about the highest forms of abstract art. Right? If you're threatened, if your security is threatened over here, you're probably not thinking about highest form of abstract art, right? Self-actualization. It's very intuitive, but this hierarchy, which he really put a framework into, had a lot of influence in psychology, sociology, politics, economics, a lot of fields. And I like applying it to computing science also. this basically means that, I think this applies to computers potentially also. Basically, we really need to start with reliability and security. If your fundamental hardware component is not reliable and secure, maybe you don't really care about what it does in the end, because it's going to be compromised, and what it does may not be useful for you, or maybe somebody else will take advantage of what it does, even though you may be thinking that it's working, solving the problems for you, right? So that's what I like applying this to. But I recommend reading books written by him also. This is another picture that I use to motivate this sort of security, reliability, safety issues. This is another example where an unreliability problem in this bridge may actually lead to both security and safety problems. Does anybody know where this bridge is? Yes?
I don't know where it is, but I know what happened.
You know what happened? What happened to it?
The engineer didn't think about resonance, and because of the wind, the bridge became too...
Yeah, basically it was doing this, galloping Yordi, that's the name actually.
Then it's amplified, and the bridge totally...
Yeah, like this. You can watch a video of it actually. Did you watch the video online? Yeah, this happened in 1940. The bridge was built 6 months. After the bridge was built, it collapsed 6 months later because of aerostatic flutter essentially, and people were trying to fix it while it collapsed actually. So I was doing this for a long time, which is interesting. You had some comment?
Yeah, I was going to say, isn't that the Tacoma Narrows?
Exactly, this is the Tacoma Narrows Bridge. This is very close to where I used to work, close to Seattle. It's over the Hood Canal. I didn't cross this bridge many times, but I crossed what replaced it many times. And what replaced it was 2 bridges. So it's not just one bridge. It was 2 bridges. Now you have actually not, if one bridge breaks down, the other bridge can be used, right? So it's a fundamental principle of reliability also. It's dual modular redundancy. And you also have higher bandwidth, right? You could use one bridge one way or the other bridge the other way. Now you have higher bandwidth as well as redundancy at the same time. So these are very fundamental principles. It's not just computing architecture. But this bridge, essentially that's what happened to this bridge. I think of this as a bit flip, for example. This bit flipped and the bridge is broken and it caused a security and safety problem. And in fact, if you read the accounts, there are very interesting accounts. There was a professor who was investigating this bridge, and there was a car, and the car was the fatality, and I think there was only one dog in the car that he tried to rescue and he wasn't able to rescue, so that was the only fatality. It's unfortunate, but there are more unfortunate incidents with these bridges, as we will see later on. So I think this is really important, because in the end this is infrastructure and it could cause security problems, but computing is a much bigger infrastructure that we have in the world today. There are so many bridges, but there are a lot more computers, so it's good to think about things in perspective. Computers are everywhere, right? You don't have 200 bridges in your car, but we're going to have 200 computers in our car. And if all of them are vulnerable to bit flips, then we're going to have all these safety issues everywhere, much worse than bridges in the end. So it's good to put that thing in perspective. And I think that's why we need to be extremely careful as computer engineers, as computer scientists, when designing these systems. They need to be, even though they may be very intelligent systems, they need to be controllable, and they need to not be vulnerable to security problems and reliability problems. Another example of infrastructure, this is another infrastructure. These are folks constructing Manhattan after the World War. And you can see that there on this very fortified steel rod. They're happy, but if there's a bit flip in this thing, they're not going to be happy very soon, right? Again, this is infrastructure, and if your computer is that infrastructure, and then we're not going to be very happy very soon. So I think of security as being about preventing unforeseen consequences. This is a very general definition, of course, right? But I think we really need to be general going into the future, because we really don't know what these computers are going to deal with out in the field, for example, when you're driving or when you're really collecting information. I don't know, whatever you use the computing devices for, you will run into unforeseen consequences, and you will get bit flips, you will get all sorts of attacks. If you are not prepared to somehow defend against them, somebody will exploit those vulnerabilities. Basically, that's why I think it's very good to think about security from this perspective. If you take a system security course, I don't know how they define security, but I think going forward in hardware, you really need to think of this way. Otherwise, you may design some hardware doing something, but if you cannot adapt to some bit flips, for example, then it's going to make everything else vulnerable. You may make your software completely secure. It doesn't matter, because somebody is going to exploit that bit flip to get into your system. And that's exactly what RowHammer is about. That's why it's, I think, so scary in that sense, but it's also very exciting in the sense that it invigorates a lot of research going into the future. Yeah, keep that in mind. You may make everything else in your system extremely secure. One bit flip will destroy that security. Okay. So, this is about the DRAM scaling problem. You've seen this picture before. And if you get bit flips in DRAM, essentially you're getting bit flips in your infrastructure. And that's your critical infrastructure that's critical for your safety and security. And we've already discussed that DRAM is becoming less reliable and more vulnerable. I'm not going to go through that again. As you reduce the size of this thing, both the capacitor becomes more vulnerable to errors, reliable sensing, and the access transistor becomes more leaky, and all of the cell becomes more vulnerable to noise in general, wherever that noise is coming from. It could be coming from alpha particles, it could be coming from some voltage changes that happen in adjacent word lines, as we will see. It could be coming from, some temperature changes, some rapid temperature changes. It could be coming from some power supply noise. And if anyone can somehow control these things that affect the noise, that affect the value that you have in the cell, you can get a bit flip. Of course, control is the key operative word over here. Control meaning that if someone can predictably induce these bit flips, then they can actually exploit that as a security hole, and they can take over your system. Because if you can somehow predictably change a particular bit, you can construct an attack with that predictable change, as we will see. Okay, you've seen this picture also. DRAM is clearly becoming more vulnerable, and this is a large-scale system study that we've done with Facebook, and there's a lot of evidence in the field that error rates of newer DRAM chips that are bigger, that have more capacity is increasing because things are more close to each other, and there's a lot more noise that's induced because of how close things are and how small these cells are. And if you're interested, you can read that paper. And as I mentioned also, we built this infrastructure. When we first started looking at issues in terms of DRAM scaling, when I wrote that paper, for example, actually I wrote that paper a little bit later. We started looking into these in 2011. This infrastructure was built starting 2012. It took about some time to build this infrastructure. And this infrastructure is an FPGA board to actually test DRAM. You can see I like the fan that we used to use at that time. We have better fans now. Actually, we have better heaters right now also. But basically, we wanted to study the retention time issues, right? As I said, that's a fundamental problem with DRAM. It's a reliability problem also, and we will discuss that. It could potentially be a security problem going into the future. No one has shown that is true yet, but I believe that there could be cases where it could be exploited as well. So we wanted to understand the retention time issues. So we built a lot of infrastructure, and this is actually the infrastructure where we discovered RowHammer. You can see that it's much more sophisticated. There are many parallel FPGAs. You can test a lot of memory modules at the same time, and the heater is better. You can see a better temperature controller over there. And you know that this is open source right now, and you can use any of this if you're interested in. If you have an idea after this course, and if you want to explore something, you can use this infrastructure. And actually, that's exactly how this research happens. You have somebody has an idea, they go and explore whether that idea is true, and they validate it in this infrastructure, and that's how discovery really happens. That's exactly why we discovered this, as you remember. I'm not going to go over this, but this is one thing that can be enabled with this infrastructure. And this is the reason why we built this infrastructure, understanding the retention time issues. And we found out a lot of interesting problems with retention time. To exploit this, you need to understand the value patterns, you need to understand the variable retention time phenomenon. So we already discussed this, I'm not going to talk about that. And there are a bunch of papers that we've written that I also mentioned that I'm not going to talk about at this point, but we may get back to that at some point. Okay, this actually one of the latest ones. This was published in DSN in this June, and multiple of your TAs are actually co-authors on it. As I mentioned, the DRAM manufacturers are adding error correcting codes inside the DRAM chips today. But this actually has implications, and we really need to understand what those error correcting codes are, because they change the value that you get out of DRAM. If you really want to understand what's happening underneath, you really need to understand those error correcting codes and how effective they are in correcting the errors. So if you're interested, I would recommend looking at this paper. It has a lot of deep analysis of DRAM errors in state-of-the-art devices. You will not find this data anywhere else because usually no one else publishes this data, very interestingly. I wish there were more people publishing this sort of reliability data from real devices. And these are the state-of-the-art LPDDR4 devices. Okay, so clearly with an infrastructure like that, you can do a lot of interesting studies and understand the retention times, which was the original reason. But we also wanted to understand other types of errors that happen in DRAM. And I will talk about this later on, but we had another infrastructure which we built for flash memory. Again, it's a very similar infrastructure, FPGA-based infrastructure that can test state-of-the-art flash memories. And we also were doing a lot of studies in terms of what kind of errors you get in those flash memories. And one of the type of errors you get in flash memory is read disturb errors. And we asked the question, actually, do you get similar errors in DRAM? And to our surprise, we found out that you can actually predictably induce these read disturb errors in most DRAM memory chips. And that's the story of RowHammer, essentially. And this essentially is a simple hardware failure mechanism that can create a widespread system security vulnerability, and I've shown this to you before. So what's the problem? The problem is actually very fundamental. It's called read disturb or disturbance errors, and it's not specific to DRAM. I guarantee that it will happen in any memory where cells are too close to each other. It happens in flash memory. Actually, we will talk about some papers later on where we show that it happens in very widespread manner in flash memory. It happens in hard disks. It happens in SRAM. It happens in DRAM, and we knew that it happened in DRAM, and I'm going to talk about what that is, but we didn't know that it happened in chips that are exposed out into the field. So what is the problem? Basically, whenever you want to access memory, you want to activate the row that you're accessing. This means that you apply high voltage to the word line. That's an activate. Now you can bring the data. Now, if you want to access some other row, you need to deactivate this row. Remember the pre-charge. You basically pre-charge the array, which applies low voltage to the word line. Now you can read another row. But let's assume that you don't read another row, but you keep reading this row. Activate. You keep activating this row. Activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge, activate pre-charge. And you do this many, many times. And you do it enough times before the cells get refreshed. It turns out in most modern DRAM chips, there are some bits in adjacent rows, physically adjacent rows, that get flipped. Now this clearly should not happen, right? You're not doing anything to the adjacent rows. You're not touching them. You're just touching this one. And you're not even writing to it, right? You're basically activating it. Activation means basically connecting the access transistor to the word line such that the capacitor drains into the bit line and you sense what's in the capacitor. Basically, it's a reading mechanism. You're just reading this row, and by just reading this row, you're disturbing what's happening in adjacent cells. And that's the problem. And we call this the hammered row, and we call these the victim rows. And essentially, with our infrastructure, we showed that you can induce these disturbance errors in adjacent rows in most real DRAM chips. Basically, you need to repeatedly read a row enough times before the memory gets refreshed. So, basically, there were 3 major manufacturers' chips that we've tested, which shall remain nameless. But there are only 3 major DRAM manufacturers, so you can guess who they are. Maybe you cannot guess exactly what's A, what's B, what's C, and it doesn't matter, because they're all vulnerable, because the scaling issue that all of the industry hit at the same time. But more than 80% of the chips that we've tested from the 3 major manufacturers were vulnerable. I'm going to tell you the reasons why this is happening, but before we go into that, this is a scaling problem. Essentially, the chips that we've tested that were manufactured before 2010 didn't exhibit these errors. The error rate, as you can see, is 0. The chips that were manufactured in 2010, this is the first appearance of the errors. And all of the chips that were manufactured between 2012 and 2013 that we tested were vulnerable. And you can see that the error rates are relatively similar across the different manufacturers. And each of these points is a chip that we tested, or module that we tested from a given manufacturer. So we tested, I think, 129 modules. And I guess this was a bit lucky. Or we weren't able to induce the errors. So we will see that you can actually, if you actually find the ways of hammering in a much faster way, you can induce more of these errors. We will get to that. Maybe we weren't able to induce the errors in this chip because it was slightly stronger. Okay, so why is this happening? Basically, there are multiple error mechanisms. Any guesses, by the way? Why is this happening, you think? Why can you induce a bit flip in an physically adjacent row just by reading a neighbor row?
They're electrically not isolated.
Exactly. Yeah. There is essentially, the fundamental thing is electrical interference. You're electrically interfering with DRAM cells that are too close to each other. So access to one cell affects the value in nearby cells due to electrical interference between the cells and the wires used for accessing the cells. This is also called cell-to-cell coupling, cell-to-cell interference. It's very similar to what we've discussed in refresh, but it's a different mechanism, of course, error mechanism. So when you activate or apply high voltage to a row, an adjacent row, this is one mechanism. When you activate that a row, an adjacent row gets slightly activated as well, because you cannot perfectly isolate the word lines. And that slight activation causes the vulnerable cells in that adjacent row to lose a little bit of charge. And if you do this activation many, many times, all those cells lose charge little by little. If you can do, if the refresh interval is not short enough, the cell will deplete its charge before it gets refreshed. And it will get drained. That's the idea. Yes?
So can you only flip from a 1 to a 0 and not the other way around using this?
That's a good question. You should read the paper for more detail. So there are cases where you could flip from 0 to 1, but so it really depends on the encoding. So sometimes charge is encoded as 0, sometimes charge is encoded as 1. And the paper discusses that issue. There are some true cells and anti-cells in DRAM depending on how you encode. So 0 and 1 is really assigned to the charged or discharged state. So at the logical level, you could flip from 1 to 0 or 0 to 1. But at the physical level, you always drain the charge. Does that make sense?
Yeah, but both cannot happen in...
Both can happen in a single DRAM chip, because there are some cells that encode the charge state as 1 and some cells that encode the charge state as 0.
Right.
So you really need to understand what your chip looks like. Yes?
No, in your paper, in your study, you're intentionally doing this over and over again, but is this possible through like normal routine operation of a device, maybe like locality?
Yeah, that's a great question.
It's also in the paper.
No, it's not in the paper. That's something we cannot really talk about as much, but actually I don't know if I have the history of this, but maybe we'll talk about the history later on. But basically, this is clearly a security issue, as we will discuss. Here we're getting a bit ahead of ourselves, but your question is, do real applications do this? Right? And it turns out there are some applications where this happens, and when this happens, finding that problem is extremely hard. So imagine a case, for example, where you bypass the caches, you have uncacheable data, maybe a lock, and you manipulate that in the memory controller, and you have many threads that contend for that lock. At that point, you may get many activates in a row that stores that lock. And we have anecdotal evidence in the field that some applications actually do that. But it's a terrible thing to happen. Actually, there in DSN 2014, there was a keynote from one of the Google folks, a software engineer, was describing how they actually chased a hardware bit flip for more than 8 months. So they thought there was a software problem, they were getting a bug, but in the end they isolated that problem to be a hardware bit flip. So these bit flips that these bit flips are essentially extremely hard to find. So they cause a lot of inefficiency, if not security issues. So clearly it's not the common case, right? Clearly most programs don't do that uncacheable thing. Okay. So we may get back to that a little bit. But basically, this is one of the reasons why it's happening. Is this clear? Okay, so yes?
Which cells are you calling vulnerable? Like, how is that defined?
Basically, vulnerable cells are the cells that are vulnerable to this RowHammer problem. So there is no very good definition, yes. So it's very similar to the weak cells in refresh, right? It's not exactly the same. So how do you define a cell that needs to be refreshed more often? These are the cells that are relatively weak. So in that sense, it's vulnerable to this failure mechanism. So there's no great definition. There might be a way of inducing RowHammer in those cells. Okay, so clearly this last thing suggests that by increasing the refresh rate you can solve this problem, right? But as you know by now, we don't want to do that. That's not a good solution. If you increase the refresh rate, you reduce the probability that you can do enough activates to cause this RowHammer effect. Because you can only squeeze so many activations to a smaller refresh interval. And that's a solution, and we will see that that's a solution that's employed in the field, but that's a bad solution because we really want to get rid of refresh as much as possible. This makes DRAM scaling issue much worse if the solution increases the refresh rate. But we will see that there are better solutions to this problem. Okay, another thing that I would like to emphasize over here, going back to this scaling picture here. So this phenomenon is very fundamental. So even in these chips that were here, 2008, 2005, read disturb phenomenon was happening. Whenever you activated some row, you would electrically interfere with adjacent rows, but probably less so because things were farther away from each other. But you could do this repeated activation of a single row, and you couldn't induce RowHammer because you couldn't do enough activates to induce RowHammer given the refresh interval. At some point in 2010, you started being able to do enough activates to induce this RowHammer effect. So it's really, that's why it's a scaling problem. As cells become closer to each other, the number of activates that you need to do to cause these bit flips became smaller and smaller. And while the refresh interval kept constant, you could fit that number of activates into a given refresh interval so that you could flip the bits. That's what scaling essentially is. The number of things that you can do, basically the barrier to induce bit flips reduces over time. That's why your scaling affects your reliability. That's another way of thinking about it, and I think that's a very good way of thinking about how scaling works. Okay. So clearly this has higher level implications, as you suggested. It could really happen in real programs. It could happen as a security attack. So basically you have widespread implications to the user in the end. So we're going to talk about that. So why? Essentially, when we wrote the paper, we also released this code in our GitHub. This code is an x86 code. As you can see, it's only 6 instructions. And basically what this code does is it selects address x and y with some good probability x and y land up in the same bank. And if they land up in the same bank, it basically bypasses the caches and it bypasses the row buffer, so that whenever you're accessing x and y, you access it in a ping-ponging manner like this. Basically, you ping-pong activates in each iteration of the loop, the x and y. And if the chip is vulnerable, hopefully you'll get errors. I would recommend trying this program out. This could be a good lab, actually, maybe. Would you like that? But the interesting thing is, we will see in the paper, there's an observation that x and y, if you have a single row that's sandwiched between x and y, you can increase the number of errors. Now, Google folks that I will reference later on actually did that exactly. They basically took that observation and they said you could do double-sided row hammering, meaning you could sandwich a single row between x and y, and you would basically ping-pong activates to x and y, and then you will get a lot more errors that way. So that's why the results that are shown in this paper are not the worst-case results. You could find a much better way of row hammering. And later people have looked at different instruction sequences that you can generate in processors, and they showed that there are different types of instruction sequences that cause even higher rates of RowHammer errors. Okay, but this is a user-level program that you can run. You don't need any privileges. You don't need to be supervisor or kernel. Anybody can run this program and induce bit flips. And you can also imagine that these different rows may belong to different applications, right? You're essentially causing bit flips in some other application. You're causing bit flips in some operating system data structures. And that's essentially how you can attack the system. You cause bit flips in critical operating system structures, and then you gain write access to some location that you're not supposed to gain write access to, right? Okay, that's the idea. So when we wrote this paper, I'm going to talk about that in a little bit, but when we wrote this paper, we tested this program on real x86 systems, and we found out that you get significant number of errors, and error rates correlate with access rate. It's not a linear correlation, but for example, you get fewer errors over here, but this is just we didn't test some more aggressive AMD systems. Some more aggressive AMD systems get a lot more errors, actually. But there's nothing really special about Intel and AMD. People later demonstrate that you can get these errors in pretty much all systems, as long as you have a memory controller that can do enough activates within a refresh interval. And all memory controllers that are out in the field are capable of that. Memory controllers are reasonably good to do enough activates. And the remember, this is a scaling problem. We're in 2019 right now. The number of activates that you need to do to induce RowHammer is actually reducing right now. At the fundamental, at the low level, device level. Of course, if you implement solutions at the high level, if you increase the refresh rate, that's not true, right? If you don't change anything, the number of activates that you need is really reducing. to induce bit flips. So as a result, this is a real reliability and security issue. So why is the security issue? When we first wrote the paper, which is one of the readings that you have, the first sentence starts like this: memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. Again, this is a very fundamental principle. Whenever you're accessing memory, you should not disturb anything else, right? Even the row that you're accessing should not be disturbed, right? But this is, RowHammer is really violating this fundamental principle. And we said in the paper that you could actually induce these bit flips maliciously, and you could design a program that can hijack your computer by taking advantage of those maliciously induced bit flips. And while we were working on that, these good folks from Google Project Zero, which has discovered a lot of really interesting security vulnerabilities in software as well as hardware, they basically reported that they could exploit this RowHammer phenomenon. They like calling it a bug. I think of this as a failure mechanism, because I think this is very different from a software bug where someone forgot something, right? This is a very fundamental circuit level mechanism that you have no way of solving unless you fundamentally change the circuit. It's not like somebody forgot something. In a sense, somebody forgot something by they didn't fix the problem at a higher level, right? But it's really a low-level failure mechanism, and they showed that they could exploit this to gain kernel privileges with a user-level attack. And I will briefly cover their blog post. They wrote a blog post about it, and they also have a Black Hat presentation. If you're interested, I recommend watching that Black Hat presentation by Mark Seaborn. And this is directly copied and pasted from their blog post. I would also recommend reading their blog post. It's actually very instructive. It's very nice system security engineering, covering hardware problems and how to exploit them in the user level. And it also has a lot of insight into the system software structures. I would recommend going through that to understand actually how this attack is really performed, because this formed the basis of a lot of RowHammer attacks into the future. And basically what they what they said was they learned about the problem from our work. They replicated the problem on a bunch of laptops, and they built two working privilege escalation exploits, essentially attacks that use this effect. One of them is taking over the Google native client, which is essentially a sandbox. It's essentially a virtual machine, and you get out of the virtual machine sandbox, and now you're out of the control of the virtual machine, right? That's also very interesting. But the other one's a lot more stronger, I think. This is the other one, basically. As a user-level program, you can induce bit flips to gain kernel privileges on x86-64 Linux. And the idea, I'll give you the high-level idea. If you really want to know exactly how this attack is launched, you really need to understand the guts of the system a little bit more. But basically, the idea is to enable this user-level process to induce bit flips in its own page table entries. So you have a process, it has a page table entry. Normally it does translation and access control through its page table entry, and it cannot access some pages because the page table entry says you're not allowed to access this. Now if you're able to induce bit flips in those access control bits in your page table entry, you can gain write access to a location that you're not supposed to gain write access to, right? Now these folks went even further. What they did was they were able to induce bit flips in the page table entries, in part of the page table entries, such that they were able to gain write access to their own page table. Once you gain write access to your own page table, you basically have complete access to the system, because now you can manipulate all of the access control bits that you have on your own, assuming that you know where your page table entries are, which you can figure out with the operating system data structures, right? Those are easy to figure out because those are exposed. So that's the idea. I think it's a very nice attack with beautiful system security engineering. It's not as easy as I described, because you cannot target only the access control bits, because access control bits, let's say your page table entry is 8 bytes, access control bits are, let's say, 2 bits or 3 bits. The probability of attack would be very low if you're targeting those. Instead, what they did was they actually used a method called page table spraying. They actually created a lot of page tables in memory for a process by opening a lot of files. And they were able to change the pointers in those page tables to locations where they would get access. But if you're really interested, you should really follow how this is done. Yeah, I think it's fascinating. But it's really a single bit flip causing all of that. If that bit flip wasn't there, nobody would bother. Okay. So, and people started drawing pictures that look like this. Is it the end of memory or computing? I don't think that's true. But I like this. A very famous hacker on Twitter wrote something like this about RowHammer. Basically, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I like this keen insight that this hacker has. Like if you're stuck in this room for some reason and everything is locked, keep banging on the walls. Hopefully the vibrations will magically open the door for you. In that case, RowHammer is used for a good purpose, of course, right? In many cases, it may not be used for a good purpose. Okay. So this is actually interesting. I think there's a lot of stories that could be told over here. Does anybody know of this paper? This was published in IEEE Security and Privacy in 2003. And these folks, I actually had known this paper much earlier than we started doing research on RowHammer. And I was always fascinated by this paper. And I had no idea we would come up with a way of realistically taking advantage of what this paper proposed. So this paper basically shows that you can, if you have physical access to a machine, you can induce errors in the memory. And this is exactly what they did. They basically built a system where they would induce errors in memory by having a 50-watt spotlight bulb close to the memory. And they basically showed that if you do that, you could get out of the sandbox of a virtual machine. Basically, if you read over here, we present an experimental study showing that soft memory errors can lead to serious security vulnerabilities in Java and .NET virtual machines or in any system that relies on type checking of untrusted programs as a protection mechanism. Let's read it actually. Our attack works by sending to the JVM a Java program that's designed so that almost any memory error in its address space will allow it to take control of the JVM. All conventional Java and .NET virtual machines are vulnerable to this attack. The technique of the attack is broadly applicable against other language-based security schemes such as proof carrying code. I think this is very nice. We measured the attack on 2 commercial Java virtual machines, Suns and IBMs. We showed that a single bit error in the Java program's data space can be exploited to execute arbitrary code with a probability of about 70%. And multiple bit errors with a lower probability. Our attack is particularly relevant against smart cards or tamper-resistant computers, where the user has physical access to the outside of the computer and can use various means to induce faults. We have successfully used heat. Fortunately, there are some straightforward defense against this attack. Well, I think disallowing physical access is one straightforward defense for sure, but you can read the paper. But basically, people knew how to exploit bit flips, and I think this is a very nice paper that talks about how to exploit bit flips. But what people didn't know, how to actually programmatically create those bit flips. So the only way of creating bit flips before RowHammer was actually having physical access or getting lucky. Getting lucky is very hard because you really need to be running your program and some software happens in the right place. That's very, very, very low probability. That's why they had to do this, heating up the memory and then taking advantage of it. But you can see that experimental setup to induce memory errors, showing a PC built from surplus components, clip-on gooseneck lamp, 50-watt spotlight bulb, and digital thermometer. You can see that that's how they induce the bit flips actually. So this is also this is very interesting. RowHammer created a way of inducing these bit flips with much lower overhead. Now you can induce these bit flips remotely. You run a program that can induce RowHammer in somebody else's computer. You don't need any physical access. We will see other security works that built on RowHammer. So between 2003 and 2015, actually there's not a lot of work that really built on this. So this is also interesting from a mindset of how research works. And this also I think is very interesting from there's a barrier between software and hardware in a sense. These folks clearly had very good insight, in my opinion, as to how you can create an unsecure system, how you can construct an attack. But nobody, in a sense, took it extremely seriously because this is a lot of work, right? Who's going to go through this? And there are clearly straightforward defenses against this. So people really didn't build on this to create other types of attacks that exploit that bit flip. But once RowHammer happened, people figured out, oh, you can do this in software very easily. You don't need any of the hardware access. And then a lot of work started coming. In a sense, if people were more forward-looking, or maybe the software-hardware barrier was not so bad in the security community, let me put it that way, then maybe people have actually done a lot of research similar to RowHammer after this paper. But of course, hindsight is 20/20, right? You sometimes need really a software mechanism to induce these bit errors. But this is good to also think about, because that's why architecture is very interesting, because we can span the software-hardware boundary relatively easily. We can go into simulation very easily, forgetting about what happens in real life. And you can explore the field going into the future. You can go out into the weeds, for example. But there are some communities that are less so inclined, in my opinion, operating systems being one of them, security being one of them. They could have done that easily also. They could have simulated these bit flips. They could have created all sorts of attacks, right? But that didn't happen until RowHammer. I think this mindset is very interesting. Sometimes you really need a real bit flip. I mean, this is not unreal, clearly, but this is a lot of work. Okay, so I would recommend this paper actually to read. I really like this, and this really explains how you can actually Google folks actually do a similar thing when they escape the Google native client. This actually works as a precursor. Clearly, Google native client is similar to Java virtual machine, right? Okay, so let me go over some of the works that talk about RowHammer. I think this is more of a retrospective. If you're interested, you can read any of these works. You're not required to, but I'll give you some historical perspective. Basically, we published our source code. Google published their source code building on our source code. They introduced this double-sided RowHammer. And actually, there were some other works that showed that you don't need CL flush, cache line flush instruction. You could actually induce. So cache line flush instruction is an instruction that flushes this cache line, right? You need that for RowHammer so that you activate rows X and Y that I mentioned, right? And people said, okay, why don't we ban cache line flush such that user level programs don't do cache line flush? That's not a good solution, because people will figure out how to flush that cache line in some way, right? And they did figure out how to flush that cache line, because cache is a shared resource. Now you can actually run another program that's kicking, or you can, in the same program, you can kick out your own cache lines, right? This is relatively easy to do. Actually, you're going to build a cache lab. You will see that how a cache works. And you can clearly figure out and build a program that can kick out its own cache lines by reverse engineering the structure of the cache. And that's essentially what these folks did. They said that it doesn't matter whether you ban cache CL flush, we can do this attack still. And the same, some other folks actually introduced the same things over here. They also showed CL flush free RowHammer. And these folks over here, actually, I'm going to talk about this very briefly, but these folks show that you can design a fully automated attack that requires nothing but a website with JavaScript to trigger faults on remote hardware. Basically, if you have JavaScript, you can actually execute remotely, and you can take over a machine that's running that JavaScript. Okay, well, we'll not go into that detail, but essentially they conclude that they can gain unrestricted access to systems of website visitors. Yes?
So is there something done today in order to prevent this?
We'll talk about that. We'll get to the solutions. Let's talk about the fun part of it first. This is a fun part, actually, because there has been a lot of recent work in security community, and security community has been fascinated with hardware security issues, and RowHammer is an early one. Later, Meltdown and Spectre came. I'll give you a story of that also very briefly. But we will talk about solutions also. But for example, these folks show that you could do software-based solutions, but we will talk about potential downsides of it. They basically monitored the solutions, but we'll talk about solutions later. So these folks showed that you could actually exploit RowHammer and memory duplication to overtake a browser, for example. For example, it's the first reliable remote exploit for the RowHammer vulnerability. Anyway, I'm not going to go through all of these, I think. They're interesting titles, as you can see. Okay, these folks also showed that CL flush free RowHammer. I think it was around the same time. That's why I included it. Okay, you can see that once you have these bit flips, you can actually create a malicious guest virtual memory, and it can have read and write access to arbitrary physical pages on a shared machine. If you're running two virtual machines, one virtual machine can access the private space of another virtual machine in the cloud. That's not supposed to happen, really. Basically, you break this isolation boundary. And the fundamental reason is you're breaking the isolation boundary, that isolation principle. You're not allowed to change. You should not be allowed to change some other memory location by just accessing this memory location. Right. Okay, so let's see what else. There are interesting other interesting things. Basically, you could do RowHammer on cryptographic keys, and there are some works that show that you could do this on DDR4 devices, even though DDR4 is supposed to have some protection mechanisms. There are some other works. You can see the claims over there. I'll talk about this briefly later on. I like this one a lot, actually. Okay. Okay, I'm going to go through this relatively quickly. There are a lot of interesting ones, and I haven't covered all of this actually. I haven't covered all of the works. If you're interested, you should read the RowHammer retrospective paper. But let me talk about this one. Actually, the first people who were really interested in the RowHammer problem were people who were writing memory testing programs. So whenever you start your computer, there's a memory testing program that can run once in a while, right? That basically scans all of memory to find the errors. And these folks, MemTest86, they basically designed a test after reading our work. That's what they say over here. After they released the software, they started getting a lot of reports from customers complaining that they were getting a lot of errors in this hammer test. And they had to write this basically. The errors detected during test 13, albeit exposed only in extreme memory access cases, are most certainly real errors. It's interesting, right? So it's interesting that they added a test, first of all. I think it's good that they added the test. Their test doesn't capture everything because, as we mentioned, you really need to, if you really want to get the maximum number of errors, you really need to find the best sequence of instructions. And you really need to map your accesses such that you do double-sided row hammering. Their test doesn't capture all of the errors, but even then, even though it didn't capture all of the errors, they got a lot of complaints. So they had to publicly write this on their website. So these are real. And this is actually interesting. I would recommend reading what they wrote. These were some of the first folks that reacted to what we've done. Okay, so this is what we said in our paper, basically. We basically construct a proof of concept. And I'll go through some of these works that I mentioned briefly, but these folks were one of the first to show you can gain unrestricted access to systems of website visitors. This is another paper. I'll spend some time on this. It's a bit interesting. People were thinking, can you do this on an ARM processor? And we had no doubt that you could actually do this on an ARM processor because in a memory controller, as long as you have enough activates that you can send to a memory controller, you could do this. But these these folks were the first to show that you could do on ARM processors. But what they did on top of that was more interesting. Basically, they showed that you could gain control of a smartphone deterministically. I think they may still have their Android application. If some of you are using Android phones, you can try it out. What they did was they had this Android app. The Android app was scanned a phone's memory. It figured out which parts of the phone was vulnerable to RowHammer. And basically, so you could do the scanning over time. The key is doing the scanning without getting detected, of course. So if you have defenses, maybe you'll get detected. Assume that you're not detected, and they were not detected because there were no defenses against it. Now, what do? You know some parts are vulnerable to bit flips. What these folks did was they figured out that the operating system in Android was allocating pages deterministically, meaning that they could reverse engineer the complete algorithm. And they actually used this understanding of how the page allocation was done to fool the operating system by changing the memory allocation patterns that you do in this Android app, malicious Android app. They fooled the operating system to allocate a page table entry to a location that they knew was vulnerable to RowHammer. And then they hammered that location, and then they gained deterministic access, kernel access to the Android phone. That's the idea. It's beautiful system security engineering. Of course, it's not an easy attack to launch. It's a probabilistic attack. All of these attacks are probabilistic attacks. But once you're able to do that, you can do that because operating system's memory allocator is doing allocation deterministically, and you can always fool the operating system to allocate a page table entry if you know what you're doing in a location that you knew is vulnerable to RowHammer. So I'd recommend reading this paper if you're really interested in system security engineering. It spans across the stack really nicely. Okay, and then later people showed that you can do these attacks much faster with a GPU because GPU has the ability to access memory at much higher bandwidth. And people also showed that you could do these attacks on a remote machine if you have the remote direct memory access interface that enables you to actually load or store data into some other machine's memory. That's the RDMA interface. They showed that you could do this attack through the RDMA. You could basically hammer a remote machine just through this interface, which is a bit sad, I think, but it's doable. And these folks show the same thing exactly at the same time, but these folks were a little bit late. This paper was published at the top place, but this paper was an archive paper because they were competing with each other a bit. They had the same idea. And this is one of the more recent ones, I think. These folks showed that with RowHammer you can actually leak secret information. As opposed to taking over the system, they showed that you could leak information. But you can read the paper. You can see that it's coming up in 2020. And there are some attacks that look at adapting this to flash memory, but we will talk about that later on. Okay, so maybe this is another attack to the system. If you're sick of these bit flips, this could be an attack or a solution, right? I don't suggest this, but I've seen this picture as in one of the articles that talk about RowHammer. I think people are very creative with pictures, as you can see. Okay, so let's talk about solutions a little bit later. But before, I think let's talk about understanding. But keep in mind as this is a solution. Any questions so far? We're going to talk about a little bit understanding RowHammer, like what's happening underneath, and build a little bit more understanding, and then we're going to talk about solutions. No questions? You already asked some good questions, some forward-looking questions. So let's see. Let's continue. So let's go a little bit deeper. So why is this happening? Actually, the error mechanism is not so simple with RowHammer. This is actually something you will not find by doing circuit-level simulations. That's the interesting part. You really need to be anticipating this going into the future. That's one of the reasons why these things slipped into the field, I think. So the error mechanism, electromagnetic coupling, we discussed this, right? You have coupling between different word lines. There's too much electrical interference between them. As a result, you're slightly opening adjacent rows. But there are other mechanisms that I'm not going to go into detail. You're going to read the paper anyway for your review. But there are conductor bridges that could get formed across rows that enable leakage. And there's also something called hot carrier injection. Basically, you inject hot carriers and the cell may become permanently damaged. This happens under extreme circumstances. RowHammer is actually a combination of these effects, an interesting combination. It's very hard to model with circuit level models. We discussed this a lot with many manufacturers. Actually, the original RowHammer work we did together with Intel folks. We started doing this work in around 2012 with Intel folks, and Intel actually filed a bunch of patents to protect against RowHammer at the same time. And we referenced those patents at the same time when we published our paper. But this is also confirmed by now at least 2 manufacturers, the fact that it's a combination of these effects. And it's very difficult to model it at the circuit level. So you really need to observe it in real devices and somehow project how many activates you really need to do in the future to actually induce RowHammer. So one way of testing, so it's also a very difficult thing to test, right? You really need to hammer a lot of your memory to find out which parts is vulnerable. You could say DRAM manufacturers should do a lot of testing, but that's a lot of testing cost to figure it out. If you cannot model it with circuits, what's left is testing. And if testing is very expensive, that becomes a lot of burden on the manufacturer. So they really need to somehow build a high-level model that says, okay, I have read disturbance effects, and I need some number of activates, let's say 1 million activates in technology node X. When I scale down to technology node X plus 1, reduce the size of the circuit, that activates will scale linearly, let's say. I'm not suggesting that's true, but you build a model. And over time, you figure out how many activates you are able to, how many activates lead to RowHammer, and you figure out your refresh rate according to that. And if you find out that you can fit that many activates in your refresh interval, then now you're vulnerable to RowHammer. So people could have found out this by modeling at a high level, but of course hindsight is 20/20, right? If you look back, I think this is the right way of thinking. Yes?
Do we know if all the cells in all the RAMs are equally susceptible?
No. It's definitely not true. There are some cells that are a lot more vulnerable, just like the leakage behavior, just like the retention time behavior. There are some cells, it really depends, basically. So you really need to profile a device to figure out what's vulnerable. And that's one of the difficulties in attack. You cannot say, okay, this device is going to be the same as this device, because it's also a matter of process variation. Okay. So we did a lot of studies with our infrastructure. Actually, this is the infrastructure where we did the RowHammer studies. But we tested 129 modules. And if you're interested, you can take a look at them. And essentially, most of them are vulnerable. Let me give you some interesting results. Let's start with this one. This basically shows the row address difference between the aggressor is the hammered row, and victim is the row where we observe the errors. What is the difference in terms of row addresses? So what does this mean? This means that memory controller is issuing an address to memory. You're activating row address X. If you're seeing errors in row address X minus 1, we're recording that as an error. If you're seeing errors in row address X minus 3, we're recording it as an error. That's the idea. And we want to understand this to see whether there's some correlation between the row addresses issued by the memory controller and the errors that we see. And this is what we get. Basically, these are three different manufacturers, worst devices you see in 3 different manufacturers. And you can see that most of the errors happen in addresses that are adjacent. So if you're issuing activates to address X, you're getting errors in address X minus 1, X plus 1, which kind of makes sense, right? But you also see that there are cases where you're getting errors in address X plus 3, X plus 7, X minus 3, and X minus 7, especially in this manufacturer. Now, what does this mean? This could mean 2 things. They could really be physically non-adjacent, or more likely, this means that there's some internal remapping that's happening in DRAM. You get address X, and it happens that address X plus 3 is actually physically adjacent to it, because DRAM manufacturers internally change the address mapping. So you essentially have a logical address mapping. Internal addresses that are physically adjacent have a different address space. And they do it for various reasons, including reliability, including, to get rid of some faults, for example, they have row level redundancy. They may remap one row to another row because that row has errors, and they may be always remapping to X plus 3. That's also possible. So the takeaway is, there are 2 takeaways. Most aggressors and victims are adjacent from the memory controller's address space perspective, but there are some cases where, from the memory controller's address space perspective, aggressor and victims are not adjacent. And in cases where things are not adjacent, the solutions may be a little bit hairy, because we're going to see some solutions which depend on knowing the address of the adjacent rows, address of the affected rows, let's say victim rows. If you can always think that, if you can always say, if this was always true, then those solutions would always work, right? I'm not saying what those solutions are. We will see those solutions. But if the victim and aggressor were always plus or minus 1 apart, it's easy. But if sometimes there is some non-adjacency, then those sort of solutions become more difficult. Yes?
Isn't the non-adjacencies one more of like a special case, since it's only applying for this one chip, and you could probably like look into the internals for like the remapping for that chip?
Yeah, so it's a special case, but this is actually just 3 modules. It exists in many modules.
Okay.
But these are just example modules. So you can think of this as multiplying with many chips, and you will see this behavior across many chips. But if you knew the internals of the chip, yes, certainly you can figure out what is adjacent and what is not adjacent. But that information currently is not exposed to the memory controllers. So this is another example where if you expose this information to the memory controller, maybe you could have a much better solution to the problem, as we will see in a little bit. Okay, so keep this in mind. I think this is very important to study. But this also points out that you have a logical address space that the memory controller sees, but you have another physical address space internally in DRAM in terms of what's adjacent and what's not adjacent. So in a real system, you have actually many mappings of address spaces. You have the virtual address space that's seen by programs that gets mapped to some physical address space that could potentially get remapped by the memory controller to some logical address space, and then that gets remapped in DRAM to some real physical address space in the end. So you have multiple levels of mappings. And if you want to take advantage of RowHammer, you really need to understand those mappings across the entire system. Yes?
I mean, if we're talking about remapping, still the ones that are like -1 and +1 in the EE manufacturer are like more significant than the other ones, no? So it's like those 2 ones at -1 and +1 are still more than +3 and -3 and +7 and -10.
Yeah, that's true.
So I would say like maybe those are still physically adjacent, but in that manufacturer specifically, the effect like goes further. Maybe like this coupling, the current that is like injected in the other word lines. I don't know, maybe it's worse in a broader like.
Yeah, that is true. That's a possible conjecture, but we haven't seen in these chips that case.
I mean, the remapping is right. I mean, I would say. But the thing that I'm seeing here is that still -1 and +1 are more significant than the other ones. So probably those are like.
Yeah, I mean that is true, but that's not what we've seen. Basically, you can induce errors in some non-adjacent cases, certainly, but most of the time it's really the physically adjacent ones. So I understand what you mean. Basically, you could potentially affect multiple adjacent rows, not just in the physical part, not just x, but x plus 1, x plus 2, x plus 3 at the same time. But that's not exactly what we see. Okay, so let's take a look at the next one. This one is actually looking at the access interval, how frequently you access the aggressor, how frequently you activate it. And in the chips that we've tested, this is not allowed by the DRAM standard, so you issue activates every 55 nanoseconds. So that's the worst case activation rate, fastest you can activate. Clearly, if you increase that rate, you can do fewer activates in a given refresh interval, right? Which means that your error rate should reduce as you increase the access interval. And that's exactly what we see. That's a good way of validating. So error rate reduces. It reduces at to different points, as you can see. So there's some, but in the worst case, basically, you need to increase the access interval to 500 nanoseconds to get rid of every single error you see in the system. So this sort of simple, naive solution will not work because this causes a lot of trouble, I think. You cannot activate a row again until after 500 nanoseconds. This affects performance. So you don't want to do this sort of naive solution. Okay, but clearly that's one potential solution. If you access the same row less frequently, you can lead to fewer errors. But you don't want to disallow the memory controller from accessing it because there may be legitimate reasons why you access a row again and again, right? For example, you access a row, you get some data out, and then some bank conflict happens and you need to access some other row in the same bank, let's say row A and B. And now you need to, you access row B. Now you need to access row A again, and you keep ping-ponging between A and B just because your access pattern is that way, right? In a real application. Now, if you increase your access interval for every single access that you see, then you will actually degrade performance in those bank conflict cases. And bank conflicts are really the cases where you really need high performance, actually. You really want to activate the next row faster so that you reduce the impact of those bank conflicts. That's the idea. So you don't want this broad solution that disallows or increase the access interval to a given row. In fact, DRAM performance is normally measured with this row-to-row activate delay, row cycling delay. So you really want to reduce it as much as possible if you want to improve latency. Okay, the next one is refresh interval. So this is something you would expect. Probably 64 milliseconds is the default refresh interval in the devices that we tested. Clearly, if you reduce the refresh interval, you should get fewer errors because you're refreshing more frequently. And if you increase the refresh interval, you should see more errors. And that's essentially what we see over here also. This is the curve. It looks kind of nice, right? It actually follows a good curve fit over here. But if you want to get rid of all of the errors by increasing the refresh rate, our results show that you need to increase the refresh rate by 7x, which is really bad, right? You don't want to increase the refresh rate. We actually want to get rid of refreshes. And remember that our mechanisms are not the worst in terms of inducing RowHammer. If you actually use Google's test and the later tests that were developed to induce RowHammer, the 7x probably increases to 10x or maybe 11x. I mean, they haven't done the study as rigorously as we have done, but their attacks are much more powerful. Okay, so clearly this is one way of solving the problem, but this is probably not the right way of solving this problem because this is really inducing a lot of burden into the system in terms of energy and performance and quality of service. Okay, so this is something that we've discussed in terms of retention time. Data pattern actually affects these errors significantly because, again, we have coupling, electromagnetic coupling, and whatever the different types of data pattern that you use lead to different types of errors. So this sort of data pattern in this case induces a lot more electromagnetic coupling between adjacent rows and at least an order of magnitude more errors whenever you do the hammering. Of course, it's not as simple as this because this goes back to what you asked, whether a cell stores charge state as 1 or 0. So if you really want to increase the number of errors, you really want to understand the characteristics of your device and figure out how do you maximize this coupling. But our results show across many devices, in general, this row stripe pattern leads to an order of magnitude, but this doesn't mean that this is the worst case pattern. There could be worst case patterns that you come up with that increase the error rates. And this is an area that was not studied as much in many papers in RowHammer. Okay, and this is expected because your charge levels in adjacent rows determine how much coupling you have. Okay, there are a bunch of other results in the paper. I'll go through some of these relatively quickly. This is an interesting one. Basically, weak cells, the cells that are that leak data very quickly, that need to be refreshed more often, there's almost no overlap between RowHammer vulnerable cells. So these are completely different failure mechanisms. Even though both mechanisms are charge-based, one is really a leakage mechanism through the access transistor, but the other is really an electromagnetic coupling mechanism that causes the leakage. So the cause of leakage is very different. One is just static leakage that happens through the access trans. The other one is actually electromagnetic coupling that is due to this active hammering that happens. So it's very good to keep these things in mind. It was amazing actually that there was almost no overlap between these two types of cells, to me at least. But it's very good to verify that with real devices. So errors are not strongly affected by temperature. This also indicates that this is really not a traditional leakage mechanism, static leakage mechanism, because as we talk, refresh is very strongly affected by temperature. As you increase temperature, the static leakage increases exponentially, and refresh rates need to increase commensurately. But with RowHammer, temperature is not a huge effector. There is some effect, but it's not a huge effect. Although with extreme temperatures, this may need to be revised. I think there still needs to be research to be done to understand what happens under extreme temperature conditions. Okay, errors are repeatable, and this leads to the security problem actually. Across many iterations of testing, the cells that we see, if you can induce RowHammer in a cell, you're able to induce RowHammer again and again and again and again and again, and that causes a security problem actually. If this was not true, if errors that you get were random all the time, then it's very hard to really create a security attack. Right? You could potentially, if your error rate is high, but if you are able to isolate the same bit, and if you attack that bit, it's a lot easier to construct a security attack. Okay, this is interesting. We see as many as 4 errors per cache line, which means that very simple error correction techniques that can detect 2 errors is not enough. They cannot prevent all errors. So you really need stronger error correction mechanisms if you want to protect this through error correction. As we will see, that's not a good solution actually, because if you remember our discussion earlier, error correction is very good for random errors, right? If you don't know the cause of an error, if it just pops up randomly, you protect all of your memory and you're guarded against that random error. But this is not a random mechanism. Clearly there's a very clear access pattern that leads to this error. So there's a fundamental distinction between random error, randomly occurring errors, versus access pattern dependent errors. And in general, if your error mechanism is access pattern dependent, then you should be able to create much simpler mechanisms to defend against them. And we will talk about that. And these broad mechanisms that help you with these broad error correction mechanisms that normally help you a lot with random errors are probably not a good idea because they have a lot of overhead. They have a lot of interesting stories over here actually. This ECC is interesting because, well, let me give you 2 stories. One is people thought that you could not do RowHammer on chips that have ECC or modules that have ECC. I never believed that. Actually, people who worked on RowHammer never believed that. But some people think that ECC is not doable. And recently, in 2018, folks from Vrije University in Amsterdam actually constructed a very nice attack where they actually showed that you could take over a system that has ECC in it. I think it's called ECC ploit or something like that. If you search for it, you'll find it. I don't think I have it in these slides. I should add it in these slides also. But that's a recent paper that showed that. Why? Because it's obvious. If there's data that shows that you get more errors than ECC can detect, then you should be able to find a way of attacking that system. And again, remember that these are errors that we get with our simple attack mechanisms. People develop much better attacks over time. Maybe you get more than 8 errors per cache line right now. I don't know. Okay, there's another story over here actually. Let me tell you that also, even though we don't have a lot of time and we're not going to complete RowHammer this time. But I present actually, I was invited to give a talk in the International Supercomputing Conference in Frankfurt like 4 years ago. And I presented RowHammer, and I think people in supercomputing should be very worried about this also, potentially. I presented this RowHammer and said that this is a problem. And the next person who was presenting after me was from Micron, a memory company. And actually, he's a good guy, but he's now retired. But what he said, his talk was not about RowHammer, clearly. But probably he was not happy with the with the fact that we talked about RowHammer. What he said in the presentation, the first sentence was, "I have a solution to RowHammer, ECC." And I never believed that. I didn't challenge that at that point in time. But our paper actually talks that this is not a good solution. And it's good that people later proved that even if you have ECC in a module, you could actually take over the system. So ECC is really not a good solution to RowHammer. It's very fundamental. If you know the error mechanism that you have, you're much better off adapting your solution to the error mechanism. If you don't know the source of your error, by all means, go and do ECC. So variable retention time, for example, we don't know the source of those errors. Those happen randomly, completely. And it makes a lot of sense to protect all of your memory. Again, soft errors. You don't know where software will happen. It happens perhaps because of a particle strike, right? You have no idea. You cannot model it. Again, it's random. So ECC is great at those things. But these things, if you see these are very repeatable. If you see as many as 4 errors per cache line, first of all, existing ECC mechanisms are not even correcting these. But this is also a very high overhead solution. Okay, so we'll discuss more about ECC. Okay, you see that there are a bunch of cells and a bunch of rows that are actually affected by aggressor. This actually goes to what you said over there. There are some rows that are affected by the aggressor in some extreme cases, but I'm not going to talk about that now. And this was actually the other observation. Cells are affected by 2 aggressor rows on either side. We didn't exploit that in the paper, we just observed that, but later Google folks exploited that to do this double-sided hammering. I think it's fascinating. I can talk about RowHammer forever, I think. And this is the paper that really introduced the problem. Any questions so far? We're going to get to the solutions soon. Okay, maybe you want me to go to the solutions. And we've written some more papers. This is the most recent paper that covers all of the work that we know of at the time, although even this is out of date now because there are more works that happened after we wrote the paper, clearly. But this is a good overview of what has happened in the last 5 years. Now let's talk about solutions. Solutions are really interesting also because you really need 2 types of solutions. One is immediate, because the problem is immediate, right? There are chips out in the field that are vulnerable. How do you protect them? Protect the vulnerable DRAM chips. Clearly you have limited possibilities because people didn't anticipate this to happen. Meaning that people didn't anticipate unforeseen consequences related to memory, going back to the security problem. If people anticipated, maybe you could have a more intelligent memory controller that you could program or that you could reconfigure somehow so that it detects these access patterns somehow, or it basically does something when there's something suspicious. We will discuss some of those solutions. But if that's not the case, if the memory controller is very rigid, what do you do? Longer term, of course, you have a lot more solution directions because you can protect the future DRAM chips and you have a wider range of protection mechanisms that you can implement in the memory controller, DRAM chip, and we're going to talk about that also. And in the paper, we propose both types of solutions, 7 solutions in total. I'm not going to cover all 7 over here. I'm going to cover the best solution that I think is also important. It's already employed in the field in some form. But maybe not in the best form, not in the form that we actually envisioned, but it's still employed. So these are some potential solutions. I think these all have downsides, like making better DRAM chips. Clearly, if people knew how to make better DRAM chips that are not vulnerable to the redisturb effect, they would have done it. But there are reasons why they cannot do it, because usually the reason is cost. Well, one is basically don't scale into smaller technology nodes, but then you don't get the benefits of smaller technology nodes. The other thing is you can have much better electrical isolation materials, but those are usually expensive. And as a result, it's not very easy. Of course, if you can come up with a way of doing it, I think this is good, but this is a very fundamental problem. All memories are vulnerable to this effect in the end. DRAM is very special. Even though all memories are vulnerable to this effect, like SSDs, flash memory, and what is the other memory? Hard drives. You cannot exploit it like RowHammer because there is no easy way of inducing read disturb at a hard disk, right? Because there are layers and layers of software stack that you need to go through. But having a read disturber in DRAM that gets those errors immediately exposed to the software. You have a data structure, an array in DRAM, and you're immediately exposed. You can immediately change a bit in main memory. So that's the big difference. So even though all of the memories are vulnerable, the implications on the system is very different if you can actually induce this error in your data structures, which is what's essentially happening. Okay, refreshing frequently, as we discussed, is not a good idea, at least if you do it across the board in all of your memory. Sophisticated ECC, I say sophisticated. In the paper we didn't say ECC because the existing ECC mechanism is not enough. If you do sophisticated ECC, yes, you can correct these errors. Like let's say you correct 4-bit errors, but that's a lot of overhead. In existing DRAM chips, the manufacturers added ECC, but they're actually detecting these errors. They're not even correcting these errors. So we actually, if you read that paper that I mentioned in DSN 2019, that reverse engineers the ECC mechanism. And the reason they've added this actually for retention time reasons, the variable retention time being one of the major reasons, not RowHammer. So access counters, this is actually interesting. Basically, somehow, can you keep track of which rows are accessed very frequently in a given time and not allow access to those rows, or refresh the adjacent rows, or refresh the entire bank more frequently once you detect something fishy is happening to some row. I think that's a very interesting solution. I'm not going to rule this out entirely, but figuring out a way of doing this at low cost, low power, and low complexity, I think this remains to be seen. The solutions that I've seen in the field are going toward that direction, but some of the solutions have very high overhead. This is basically understanding. In the paper, we kind of dismissed this solution. I think that's not. I think the solution still has more merit than we give credit for in the earlier paper. In the later paper, we fixed the problem, saying that I think there is more merit to the solution. If you can somehow do this efficiently, I think this could potentially be a good solution. But I'm going to propose some other solution. Yes?
Yeah, could you perhaps use the refresh solution, but from a different scale? For example, refreshing only the adjacent rows, and then maybe use that information not to refresh it if the frequent refresh is like soon coming?
Okay, that's a good point. We're going to talk about that. Let's see. I like that solution, basically localizing the refresh. Yeah, across the board is not a good, but if you localize it and if you do it intelligently, I think that's a good solution. Okay, so these are naive solutions. Basically, you don't want to throw all accesses. We discussed this. You don't want to refresh more frequently. But if you want an immediate solution, you're basically stuck with this, I will say. Maybe not 7x. So basically, the level of controllability or change that you can have in existing memory controllers is you can change the refresh rates. Basically, you can have a software patch that changes the configuration of the memory controller that can increase your refresh rate. And that's essentially what people have done. This is an example. Apple has released a security release where they say a disturbance error, also known as RowHammer, exists with some DDR3 RAM that could have led to memory corruption. This issue was mitigated by increasing memory refresh rates with this security release. Essentially, you should probably download the security release to increase your refresh rates and expend more energy and more performance. But of course, you don't want memory corruption, right? And I like this security release because Apple was nice enough to credit academic work. Not many companies are actually nice enough to do that. I think people should be better in terms of crediting where they learned the information from. But everybody employs the same solution essentially today because that's what you can do in the field. There's no other solution. At least this is the easiest solution. There are some software solutions that are proposed that, for example, you keep profiling the performance counters and you try to guess whether a row is being accessed very frequently, but that's a lot more intrusive, right? Now you need to do this profiling. There needs to be some program running profiling and figuring out whether some rows are accessed frequently. And that's not an easy solution. That was proposed in research, but it's not employed in the field because there's a lot of overhead. I think software solutions are good to examine. Maybe they will lead to some other benefits, but I don't think those are, in the end, good fundamental solutions to this problem. Okay, basically, other vendors definitely release similar patches. So let's talk about the solution that we proposed in the paper. This is actually a probabilistic solution. And the idea is very, very simple actually. after you close a row, you activate, in other words, refresh, one or both of its neighbors with very low probability. And that's the idea, basically. And you set the probability to a level that you're comfortable with. And if you do that, we've shown that you get a very good reliability guarantee that prevents RowHammer. And if you're not comfortable with it, increase the probability, right? And over time, if you require fewer activates to actually induce RowHammer, you keep increasing the probability, right? Now this is a better solution than refreshing the entire module, clearly. You're just refreshing adjacent rows. And you're doing that at low probability. That's the idea. And this is actually very low overhead in terms of power, in terms of performance. It's stateless. Stateless is maybe too strong, but it's stateless in terms of you don't need to keep track of which rows are being accessed. You just need counters to keep account of when you need to do the refresh. And it doesn't need to be even probabilistic, actually. It doesn't need to be random, even though we use random in the paper. I think it can be deterministic also if you increase P. But it's basically low cost and low complexity. And we show that it's a low cost and effective solution. But let's take a look at where it's implemented. Actually, in real systems, it's done in both cases. Not exactly in the way we described, but it could be implemented in the DRAM chip. I think that's not a great place to implement it. Why? Or if you need to change the interface if you really want to implement it in the DRAM chip. But today, basically, there's a lot of slack in timing parameters. For example, let me give you a hypothetical example. Whenever you do a pre-charge, which means that you're closing a row, the manufacturer specifies the pre-charge take 15 nanoseconds. But in reality, the pre-charge takes, let's say, 2 nanoseconds. Which means that there is a 13 nanosecond slack. And they can sneak in a refresh to an adjacent row in those 13 nanoseconds, right? Of course, that's the idea, basically. You may need to change the DRAM timing a little bit internally. But if you do that, now you refresh the adjacent row by exploiting the slack in the timing parameters. Basically, DRAM manufacturer put a lot of guard band to the latency for whatever reason. We will discuss that later on. And they're exploiting this guard band to fix a reliability problem. And this is employed in, actually there's a lot of slack in DRAM chips timing today. And a para-like solution is kind of employed in existing DRAM chips, although it's not the exact same solution. Okay, I don't think it's a good place. Actually, we will later see that we want to get rid of the slack, because that slack is also inefficiency, right? Why are you waiting for 15 nanoseconds when the thing is done after 2 nanoseconds? That's one of the causes of that latency curve being almost flat over 18 years, if you remember that curve. So we want to get rid of that. So this is, in a sense, cheating. It's really exploiting this additional slack that you put in and recovering back for reliability. But I think going forward, a better solution is really doing this in the memory controller. Memory controller basically figures out, not figures out, but let's say every 1,000 activates, it decides to refresh the adjacent rows. But of course, if you want to do that, now you need to know which rows are physically adjacent. That's where the picture that I showed you earlier comes in. The memory controller, if memory controller doesn't have this information, you don't have complete protection, right? The memory controller can guess. Most of the time, address x plus 1 and x minus 1 are physically adjacent. So it can actually do that, refresh. But it will miss cases where x plus 3 is adjacent to x. Right? So this requires better coordination between memory controller and DRAM. Somehow the memory DRAM chip needs to expose which rows are physically adjacent, or at least expose that function, so that the memory controller can issue the refreshes to the real adjacent rows. Does that make sense? So this is a solution that cannot be also easily implementable without changing that interface. But I don't think that interface changes that much. Usually when a system starts up, it reads some information from some non-volatile memory that's on a DRAM module that tells the characteristics of that DRAM module to the memory controller, and the memory controller sets up the timings and everything. You could actually store that information, that non-volatile memory that's on the DRAM module, and give that information to the memory controller. So it's not that bad, actually. It's relatively easy to do, but it requires a change of mindset. The manufacturer needs to expose this information. DRAM manufacturers tend to be very, very conservative. If you want to get to know very conservative folks, talk to DRAM manufacturers. I'm just kidding. There are very, very forward-looking folks also in the DRAM industry, but usually they tend to leave to other companies. Sorry. Okay. So let me. The good thing is the industry is moving in the right direction over here. Basically, if you look at this is a recent memory controller by Intel. And in the BIOS, you can pick your RowHammer solution. You can pick your 2x refresh, or you can pick your hardware RowHammer protection. And the hardware RowHammer protection, you see that you have an activation probability that you can set. So basically, every other activation, you do a refresh to the adjacent rows. And the adjacent rows are defined as x plus 1 and x minus 1 in this case. So memory control issues that. Of course, that's a bit overkill. Probably you want to do it over here. Every 2,000 activations or so, you issue adjacent rows. And this is user settable. It's a little bit different from what we imagined, clearly, but it's exactly the same idea implemented at the BIOS level. You could set your RowHammer activation probability, probabilistic adjacent row activation probability at the BIOS. Ideally, the system will do it without involving the user, I think. Does that make sense? But the good thing is, industry is moving toward that direction. Essentially, they're realizing that you need more intelligent control. And this is slightly more intelligence, as you can see. Maybe user-guided intelligence, but it's still intelligence. Okay, any questions so far? I don't think we're going to finish what I have in the last 3 minutes. So maybe this is a good place to take some questions. Yes?
Is there a further attack against this?
Against para?
Yeah.
Okay, now you have a good mindset. How can you attack this solution?
I don't know.
You don't know? As far as I know, there is no attack that's developed against it. Because you can always set your probability to be lower. I think the downside is you need to know how to set your probability, right? That's important. Yes?
How do you effectively evaluate your probability without having too much overhead?
So basically, one way of doing this is every 1,000 activates, you do a refresh, right?
But that's, I think, isn't that deterministic? So you could exploit that.
So
every 1,000 activates, you go somewhere completely else.
Exactly. So if you could somehow do that, now you're thinking you also have a good mindset right now. Can you actually exploit that? I don't know. That remains to be shown. I think deterministic is a little bit dangerous from that perspective. You're right. Maybe you change it a little bit, right? So in the paper we did it completely random. We assume that you have some random number generation mechanism and randomly, and that random number provides a set bit to you every, let's say, probability. And there's some overhead for that, clearly. But actually, we will later see that you can generate random numbers using DRAM as well. But this is actually a good way of thinking. Can you? I think if you reduce your probability enough, then I don't think you need to be random. But of course, your overhead increases because you have to squeeze so many activates, right? And if you actually try to skip some number of times, maybe you're not going to get a lot of activates that way. But I think if you introduce some sort of randomness, maybe not going completely random, but some sort of unpredictability, that you don't do it every 1,000, but sometimes you do it somewhere in the vicinity of 1,000, then I think you can solve the problem without going into a lot of random number generation overhead. Does that make sense?
Yeah.
Okay. Okay, what else? Yes?
I'm worried that user has like say in how often it changes. It's possible to make an exploit which changes instead of the user the amount of refreshes and then induces RowHammer attack.
Could you say it again?
For example, could an exploit be made which like since the user has the ability to change the rate of refreshes?
Oh, okay.
Could you make an exploit which changes this instead of the user?
So actually, the user doesn't have that ability. So refresh rate is really determined by the BIOS. But if it were determined by the user, yes, certainly. That would be another vulnerability. So the patch that I discussed that changes the refresh rate, that actually goes through the BIOS.
Okay.
What else? But yeah, I think this actually opens up a lot of good things. Basically, if you want to get rid of refresh, like the ways we discussed earlier, you really need to keep security in mind also. You cannot just get rid of refresh arbitrarily because that may actually lead to more RowHammer vulnerability. So you need to keep that in mind. But I believe that actually RowHammer solution needs to be completely orthogonal to the refresh solution. These are completely different problems. So if you solve RowHammer, you can get rid of refresh without thinking about it.
Yeah. But I'm also worried about all the software solutions which could come up exactly because of that reason, because if it's in software, it's probably exploitable in the other way. And if you exploit the solution to RowHammer in software, then you exploit it.
That's true. If you can somehow exploit the solution to RowHammer in software, then yeah. That's why you need to be very careful in designing these mechanisms. What else? Any other thoughts? There's good brainstorming. I wish we had longer class because I have a lot of very interesting material over here. But I think we're almost done. Any other burning questions? Yes?
You said that Para was the solution that you recommended and that a lot of companies have adopted it. Is that as a result of your recommendation?
Yeah, certainly. I mean, the paper that we have is the first proposal of Para. We don't know of any other proposal that's out there. There are some patents, as I mentioned. Intel actually filed some patents, but those solutions are different. So those solutions actually, there's something called targeted row refresh. It's not probabilistic like Para. Para is more automatic, if you will. Targeted row refresh, somebody sets the row refresh rate. Actually, nobody knows how it works. People are still trying to reverse engineer how it works. But those are some of the solutions that are proposed in the patents. Any other questions? Going once, twice. Okay, then we'll pick up next week from here. Have a good weekend.